Hi guys, so today we're going to create a mesh around a sphere in a far field and use it to solve in Fluent for steady state simulations, and then we will export it to CFD post and do some visualization. So the purpose of this tutorial or this video lesson is not mesh generation, but just how to export data from Fluent to CFD post, where you can visualize things much better. So let's start by creating a blocking, which we will call fluid, and click apply. Now this is fine, and this is a very simple blocking since it's a sphere inside a sphere, so you just need one OR grid. So we are going to create an OR grid using the OR grid function and select this block and maybe offset 2 times and click apply. And then we can even go to scaling again, and scaling for the first time, and scale this block still furthermore until it reaches the sphere. Okay, so that should do, and we're going to create a part called solids, which is the small sphere inside, and we declare it as it is. Okay, so that's basically everything is done. Very simple meshing, and we're going to delete this block and just give some mesh parameters. For this tutorial, I'm just going to use multiply 2 times and see until 96,000. Okay, so create pre-mesh, see what it looks like, and convert to unstructured mesh. Okay, so I got the inlet part as blue and the outlet part as yellow surface. Let me just see how many mesh elements are there. So info, mesh info, and it is 290,000. It's not too bad, but just to refine this mesh, which is going to, actually we haven't got any grid nodes here, so what I'm gonna do is just rescale it, so 0.5 and 0.5, and then just use some grid nodes here, maybe 100, and use 100 is a bit too much, 50, and use the ratio 1.2 or 1.1, and just give some small spacing close to according to your Reynolds and stuff, but I don't have a particular Reynolds of interest for this particular domain. So let's pre-mesh again and just view a scan plan to see if everything went okay. So yeah, that should do, and I'm gonna convert this to an unstructured mesh again, replace, and output as sphere CFD post. Okay, so click. So let me come back in 1 minute when it opens in Fluent. Okay, so I have opened it in Fluent and done some settings. First of all, I'm gonna check the mesh quality, and it's 0.85. Let me move this 0.854, which is really good. And so I have set up it as a steady state case with energy equation on, since we are using far field instead of velocity inlet, and the turbulence will be calculated by the famous k omega SST model. Materials will be, since we used we using far field, we have to select ideal gas, the usual air properties, and boundary conditions. I have set up that inlet will be something that I should tell before I do this. Basically, if you give appropriate names like inlet outlet, it will be recognized in Fluent as the name. For example, I gave outlet and it is automatically recognized as an outlet vent, which is good. So it was velocity inlet when I imported the mesh, but I just changed it to pressure far field, and I reduced the Mach number to 0.1 at angle of attack 0, and I just reduced the turbulence intensity and viscosity ratio. The reference values will be calculated from the inlet, and that gives us, I'm not really interested in the forces of the sphere, like the drag and the lift and stuff, so I'm just gonna keep it as it is. And the solution method will be the simple method, semi-implicit pressure linked equations. Some of them will be first order, some of them second order, some under relaxation like turbulence, viscosity and stuff. So let's go ahead and initialize and run some calculations, see if we actually get a converged solution. So I'm going to initialize now using hybrid methods. So the residuals have already dropped below -9, which is good. We'll do about 200 iterations. And it's going to take a while, so let me come back when this 200 iteration is done. But just to let you know that 200 is not enough, I just want to show the main purpose of this video is using CFD post for visualization. So I'll end the simulation at 200 and export the data to CFD post. So I'm going to pause the video here and come back when the solution is converged, or not converged, when the solution has reached 200 iterations. Right, since the residuals have already dropped below, most of them below 3 to the power -2, I think I'm going to stop the simulation here rather than even waiting for 200. But notice that there's a reverse flow on 274 phases or something like that. This is because in my mesh I have, let me pause. Sorry, I didn't mean to pause the video. Let me pause the simulation. So it is because we have the outlet. If I show you, the outlet is not appropriate. Basically the outlet has to be all this side in X direction, but I have some outlets here as well, which, because I did the mesh a bit quick, so basically the outlet's supposed to be far behind, not underneath. Anyways, it's not going to be a big problem for our visualization purposes. So let me just show you quickly what it looks like in Fluent now. So everything except the interior I'm going to display. Actually, I'm not going to display the interior outlet and inlet as well. And then I'm going to zoom in, and this is what it looks like. And this is our X direction of the flow. So the pressure is highest where it hits the sphere and lowest on top and bottom. So we can even do a field display and see what it looks like. But in Fluent, it's difficult to put planes and streamlines and stuff we can do, but it's just for a quick visualization. The professional visualization in NCC is done in CFD post. So let me just stop this and export the data to CFD post. So I went file, let me do that again, file, export to CFD post. And I'm going to select all these quantities. To be honest, if you know what you're doing, you can select the stuff that you are interested in. But for now, I'm going to write all these quantities, but except say open CFD post. Yeah, why not? Just open CFD post as well. So write and overwrite and wait for it to write the data. So the CFD post data file has the extension .cdet, whereas Fluent data file has the extension .dat. Okay, so it's writing the data and we are waiting for it to write that and open CFD post. Okay, so the file has opened with the data loaded. Now this big sphere that you're seeing is the inlet outlet. So even if I rotate, you will not notice anything, which is quite stupid to do. Okay, basically this is inlet, this is outlet. So let's face the outlet in this direction. Yeah, something like this. Well, what I'm gonna do is just go to inlet, go to edit, and turn the transparency to something like 9. Click apply. And for outlet, do the same thing. Turn the transparency to something like 0.9. Click apply. Okay, so now we got the sphere, that small sphere inside. First, we can do some simple things like let's insert a plan. So insert location. Let's insert a plan. So let's say this is the XY plan. So XY is the horizontal plane. So we insert that. This is what we have. Now let's insert a plane again. So this time we call it YZ plane. Right, and in the YZ plane, again we insert it in from the middle. So you can vary this by using this, and we can also insert a plan in XZ direction. So let's insert a plan in, let's call this XZ plan, right? And click apply. So we have, oh, I didn't choose from here XZ, so ZX plan. Okay, also I want to insert another plan just behind the sphere, which is the YZ plan. So insert location plan YZ behind, let's say 3 meters. Okay, so this time it will be YZ and it will be in 3 meter behind. Okay, that's good. And here we can insert now we have inserted some locations. We can even insert a small volume. Let's insert a small volume, that's a sphere, at 0.00000 and maybe radius of 3 meters. Click apply. Okay, so we have a sphere now there. Good. So let's untick everything now. Start from the XY plan. Let's insert a contour of velocity. Oh, okay. velocity xy. Is it xy? Yeah, xy. So it's good to give names which is appropriate. So this time xy plane, and we're gonna choose velocity. So from here the variable will be, where's that fella, velocity. Okay, click apply. Right, this is what the velocity is looking like. Since we have some reverse flow, this is why there's a increased redness here, so higher velocity there. So again, like I said, it's because the outlet is not appropriate. We don't need to have an outlet here, but unfortunately the way I did the mesh, there is an outlet. Let's zoom in and see a bit more closer what it looks like. So this is what it is looking like. Right, now untick that and insert again a counter. This time insert counter in the XY plane. So XY counter, well, where is it? In the location XY plane, and this time also let's insert velocity. Click apply. No, it's not XY plane, it's XZ plane. Sorry. Yeah, so this is what it looks like there. Fine. So we have two things now. So XY, X. What happened to this guy? It's supposed to be ZX plane. Apply. So we have two things now we have done. Even now it looks a lot better than Fluent. Now you know the velocity on the sphere is going to be 0, but we can insert the pressure on the sphere. So pressure of sphere. Okay, so the location will be the sphere, and we're going to insert pressure. Click apply. That's what the pressure is looking like. Right, fine. Let's turn off the contours now, and the surfaces as well. Let's go to insert a vector this time. So vector behind, vector of velocity behind, don't mind the caps by the way, behind the sphere. Okay, so location will be here, and variable will be velocity. Well, what happened to the sampling? Oh yeah, it's so I thought it's the count. Okay, click apply. Let's reduce this vector. 0.7. Equally spaced, maybe 400 points. Okay, so that's how you insert a vector. We can even insert a counter behind, which is going to be more appropriate on the location YZ behind. And let's see what pressure is looking like there. The pressure is quite constant. Let's see what velocity is looking like. This is what velocity is. So when you have a steady state solution, if there's any vortices behind the sphere, it will detect. So at the moment there's only two small ones, I think. So let's insert eddy viscosity. so the eddy viscosity region here. So that's how you insert a plane behind the sphere, and it's quite useful in aerodynamics to insert a plane behind the body of interest. Okay, so we've done that, and I'm gonna turn this, just keep the pressure, and we're gonna now insert on a streamline on XY XZ plane. Okay, so streamline on X, it will be a surface streamline. The surface will be ZX plane, and the variable will be velocity. And bam, there you go. This is what it is looking like. Now you can increase the number of points on this surface streamlines to make it more dense. So let's say 120 points. Yeah. So if there's any separation or anything on this, it will show. So let me just go to Y direction. Okay, this is what it's looking like. So we got the sphere. We can even reduce the what is it called? Vertices. Yeah, concentrate it to the sphere region to show the flow separation. Okay, so we have that, but what we are interested in now is just to insert, how to insert a streamline, 3D streamline. That didn't really come off as 3D, did it? Okay, 3D streamline, and start from the inlet, equally spaced, and click apply. Maybe increase the number of points to 300. Click apply. Let's rotate this guy, see what it looks like. So that's still not very concentrated on the region that we are interested in, but it shows something. So we can do forward and backward, and change this to Vortex and increase the number of points again. So let's do 1,000 points. 1,000. Okay, so that's what it is looking like. We can even insert this streamline to start from the sphere. Copy paste. Actually, I'm wrong there, so forgive. Okay, so now we've inserted the pressure and stuff. We can even go ahead and insert something called, to see where the vorticity is going around the sphere. So we can go ahead and insert a thing called Vortex coregion, and we can define it to be the vorticity, and click apply, and this is what we get. So because the vorticity is highest, closest to the sphere, so we need to reduce this value. So what I'm going to do is just reduce it to something a bit lower, maybe still a bit lower, maybe a bit too, still a bit higher than that, a bit lower. Okay, so this is how the vortices are developing behind the sphere. So that is the two vortices that's going behind the sphere. We can even insert a contour and insert velocity on this vortex coregion, so location will be vortex coregion, and click apply. So that's the velocity of the vortex region. So many cool things that you can do. So let's turn on some of the stuff that we did. So Streamline 1 is not, we are interested more in this Streamline. So let me just go and put not X but Y direction in. Okay, I think I better do it manually. So remember that this is still reverse flow is causing this, so don't be too bothered about that. It's the reversed flow causing that. Okay, this is the correct. Still not correct, so okay, and down we're gonna insert the one of the surfaces that we did. Not counter 1, 2, no. Okay, velocity XY direction, maybe. Turn this side, and maybe velocity in XY. Okay, and move it a bit below. Also maybe insert, not insert, the 3D streamline we did, the Streamline 1 or something. Okay, so we can even do other stuff like rendering. So this velocity XY, what we're gonna do is just go to edit and view. The option has suddenly disappeared, so is it this one? Nope. The rendering options that I usually use are not seen in this one, but rendering is just to make the stuff look better. Basically you can use, if you really want to render your solutions, you can, this is a good visualization in terms of flow and understanding the physics, but if you really want to render your solution, you can use Blender for that. Alright, so that concludes this video lesson.